Hey there, it's Shannon MATHCHICK Myers, and today we're going to take a look at part 4 of the partial fractions techniques of integration section. So this part is the case where your denominator contains a repeated, sorry, I misspelled that, irreducible quadratic factor. So if that denominator, polynomial q, contains a non-repeated irreducible quadratic factor of the form ax squared plus bx plus c, the quantity to the n power, where n is greater than or equal to 2 and n is an integer, then in the partial fraction decomposition of p over q, allow for the terms p at x over q at x equals. So you would have a1x plus b1 over the first power of your irreducible quadratic. And then plus a2x plus b2 over ax squared plus bx plus c, the quantity squared. And you'd keep going until you represented every power of that irreducible quadratic. So you'd have capital A sub n times x plus bn all over ax squared plus bx plus c to the n, where the numbers a1, a2, down to an, and b1, b2, down to bn are to be determined, the capital A's and B's with the subscript. Groovy? Okay, so let's take a look at this example. I'm checking, the degree. The numerator has degree 3 because of that cubic. The denominator would end up having degree 4, so we're good. We don't have to do anything weird about long division. So here we go. Would you agree that there's no sum of squares formula? Yes, great. All right. So now we'll do our partial fraction decomposition. And fortunately, I left this whole page for us. So our partial fraction decomposition will be, so we have x cubed over quantity x squared plus 16 squared equals a1x plus b1 over x squared plus 16, that quantity to the 1 power. And then we have to represent with another a2x plus b2 over quantity x squared plus 16 squared. Groovy? All right. So we will have x cubed over x squared plus 16, the quantity squared equals. Our a1x plus b1 needs 1 factor of x squared plus 16, and then our second one is good to go because it had that least common denominator, a2x plus b2 all over. Now do you see we have x squared plus 16, the quantity squared, so we can omit the denominator from our computations, and then we'll have a1 times x cubed, I'm just multiplying out right now, and then plus b1 times x squared plus 16a1 times x plus 16b1 plus a2x plus b2. All right, so now I'll have I'm going to need to add some terms in on the left. So I have a 1x cubed. I'm going to have a 0x squared, a 0x, and a 0 for my constant term. And then I will have a1 times x cubed plus a2, sorry, not a2, b1 times x squared. And then let's see, I have two terms with x's, so that would be 16a1 plus a2 times x. And then for my constants, I have 16b1 plus b2. Awesome. And so now equating, I'll have the constant on the left is a 0, and on the right is the 16b1 plus b2. The x coefficient is 0 on the left, and on the right it's 16a1 plus a2. The x squared coefficient on the right is b1, and on the left is 0. And on the left, the coefficient to x cubed is 1, and on the right, it's a1. So equating those things that we highlighted, we'll get a1 is 1, b1 is 0. (16a1 plus a2), that's a 2. And that was with the x term, is also going to be 0. And then 16b1 plus b2 will also be equal to 0. So just back substituting, I know that a1 is 1. So I'll have 16 times 1 is 16, plus a2 is 0. That's going to give me a2 is negative 16. Plugging in b1 is 0, that tells me that, in the last equation, tells me that b2 is also 0. Cool so far? And so it turns out that it simplifies this quite a bit. So if we look at, let's see, a1 was 1 and b1 was 0. So we have 1 over x squared plus 16, and then let's see, a2 and b2. a2 was negative 16 and b2 was 0. So we'll have minus 16 over x squared plus 16 squared. My apologies, it's not just going to be 1 and 16, it'll be 1 times x and 16 times x. Groovy? Because they were a1 and a2 that remained. All right, so rewriting, which is great because it would have been a lot harder to integrate. All right, so rewriting, we will have this whole integrand is going to equal to x over x squared plus 16 with respect to x, and then minus 16 over x squared, 16x over x squared plus 16, the quantity squared, with respect to x. So on this first one, we need a 2, so we'll need to multiply by 1/2. And on the second one, we could rewrite the 16 as, let's see, 8. So this 16 is going to be written as 8 times 2, okay? Because we need a 2 dx for our G prime. And then we will end up with 1/2 times natural log absolute x squared plus 16 minus 8 times x squared plus 16 to the -1 over -1 plus our constant of integration. Now take a look at the expression in the natural log. You're squaring a number, which means it'll be positive, then you're increasing it by 16. So that natural log does not need parentheses. And bringing the power in, we'll have this natural log of the square root of x squared plus 16, and then minus 8 over x squared plus 16 plus our constant of integration, and we're all done. Excellent, excellent. Make sure there's no more problems. We do have one more, which I will include with this one, all right, because it applies. We want to, there's a typo here, how to evaluate a definite integral, which requires us to decompose the rational expression in the integrand into partial fractions. So here we go. Let's see if I left nope, I didn't leave an extra page. So let's look at our partial fraction decomposition of this one, right? We will have x plus 1 over x times x squared plus 1. That's going to equal to, I'm going to write it as a over x, because I have one linear factor, plus a sub 1x plus b sub 1. Remember, a is a different variable than a sub 1, over x squared plus 1. Good so far? And you know what? I'm going to move this over because I'm looking right now and I did not leave enough space to write the result. Okay, so x plus 1 over x times x squared plus 1 equals a, and a needs the x squared plus 1 portion to get a common denominator, and then plus quantity a1x plus b1, that needs to be multiplied by x. And now we have the common denominator, which is x times x squared plus 1. Now we can just work on the numerators, and we'll have ax squared plus a plus a1x squared plus b1x. We have an x squared term, so I'm going to add in a 0x squared plus 1x plus 1 equals a plus a1 times x squared plus b1 times x, and then we have plus a. Now, things we equate. So the 0 coefficient to the x squared on the left is equated to a plus a1. The 1 coefficient to the x is equated to b1. And then the constant, positive 1, is equated to a. So this system won't be so bad, right? So we'll have a plus a sub 1 equals 0, b1 equals 1, and a is equal to 1. So plugging in a into the top equation for 1 equal to a, we'll have 1 plus a1 is 0, and that gives us that a1 is negative 1. And now we have all of them. And so this will be, a is 1, so we'll have 1 over x. And then we'll have plus negative x plus 1 over x squared plus 1. And now, coming over to the integral, we will rewrite our integral, okay? Actually, I'm going to leave a little space here. Now we'll work on the indefinite integral. So the indefinite integral of x plus 1 over x times x squared plus 1 with respect to x will be the integral of 1 over x dx. And then I'm separating the integrals and I'm factoring out a negative, and I'll have the integral of x minus 1 over x squared plus 1 dx. Now I'm going to need a 2x. The derivative of x squared plus 1 is 2x. So I'm going to need a 2 along with that x. So I need to multiply by a half. So now I will have, so the integral of 1 over x dx is natural log absolute x minus 1/2 times the integral of 2x over x squared plus 1 dx minus 1/2 times the integral of negative 2 over x squared plus 1 dx. Now, I don't need that negative 2 for, I can simplify the negative 1/2 and the negative 2. So we're going to end up with natural log absolute x plus arc tangent at x, because our a is 1, so you'd have 1 over 1 times arc tangent at x over 1. I'll leave out the constant because we'll be evaluating it, and so we'll get equal to natural log at absolute x. We don't need the absolute over the square root because we've got x squared plus 1, which is always positive. And then plus arc tangent at x, all evaluated from x equal to 1 to x equal to 2. And then we will get our upper limit of integration will be natural log. Both numbers are positive, so I can take off the absolute value. So I'll have 2 over 2 squared plus 1 is 5, so 2 over root 5. And then plus arctangent at 2 minus lower limit natural log of 1 over root 2 plus arctangent at 1 and this will give us, we'll have a natural log at 2 over root 5 minus a natural log at 1 over root 2. So we could write that as 1 happy log. The 2 over root 5 goes in the numerator because that's the positive one. and the 1 over root 2 will go in the denominator. And then plus arctangent 2, just leave it as arctangent 2, but arctangent at 1 is pi over 4, because the angle, remember the output of an inverse trig function is an angle, and the tangent function is 1 when the angle is pi over 4. Cool? And we don't look at the one in quadrant 3 because we're dealing with inverse trig. All right, so continuing to simplify that log. It can be so fun to play with, right? So we'll have 2 root 2 over root 5 in the log plus arc tangent at 2 plus pi over 4. So I'm going to bring the pi over 4 and put that one first. And then, I don't know, if you wanted to, you could rationalize the denominator. I'll do it just for the heck of it. I would have taken this last answer. Pi over 4 plus the natural log of, we would have 2 root 10 over 5 and then plus arctangent at 2. And that's our result. Cool, cool? Make this one nicer. All right. So that is it for partial fraction decomposition related to, techniques of integration. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, click on that subscribe button, like the video, maybe share the video. Bye.